Okay, guys, so again, I'm gone for tennis this time. I know I've been gone quite a bit this year, it feels like, and I'll be gone a couple more times in the next couple weeks. But here's another video lecture for you guys. So today there's kind of two parts. There's the review of the 3D surfaces for that quiz that you have. And then there's going to be the cylindrical coordinates and cylindrical equations. The lecture part's pretty darn easy. It's similar to what you did in some of the calc stuff with converting to polar, but now you're just going to convert to cylindrical, which is the 3D version of polar. But first I want to go over some reviewing of 3D surfaces for that quiz that you have. Here I'll start you with a 2D surface, or a 2D equation, and you guys should recall that this is a hyperbola. And a lot of times people debate which way it opens up. They don't know if it opens up that way or if it opens up this way. And a lot of times they just start guessing and they're like, how do I do it? How do I do it? Well, a nice thing to remember with hyperbolas is in this red case, I have y-intercepts. And in the blue case, I have x-intercepts. So you just have to ask yourself in this equation here, which one will give me intercepts and which one won't. Remember, intercepts, if I want, let's say the y-intercept, it is guaranteed to be 0, comma, some sort of y. And for the x-intercepts, it's x, comma, something, 0. Well, if you stare at the equation, make x equal to 0, or make y equal to 0, and see if you can solve them, actually, and you'll figure out which one it is. So I'll move this over for a second just for a reference. The whole concept is I need to set one of them equal to 0. Because of this negative, you have the void in y. What I mean by that is this. Try this. Set x equal to 0, and you'd have negative y squared equals 16. That can't happen. So because of that negative, there are no y-intercepts. No y-intercepts. So if you're looking at my colors again, if it was the red combo or the blue combo, it's actually going to be the blue one. Because if you set y equal to 0, that means x squared equals 16. So x equals plus or minus 4. So it's going to be the blue guy, but more specifically, it's going to be the blue guy with x-intercepts of plus or minus 4. So for a rough sketch, you know it's that and that. Okay? So the whole idea is where you find the void with that negative, where that intercept can't happen, it helps decide which way it opens up. In the 3D world, you're going to have that same idea when you're trying to open up hyperbolas of two sheets, okay? Because you want to make sure you know which way it opens up. Or a hyperbola of one sheet, and which way does that guy hover around, okay? So if you look at this equation here, we always want to recognize that they're all squares on the x's, y's, and z's. So with all of those being squares, you already can narrow it down to a couple shapes. So the possible shapes, because those are squared, are the ellipsoid, the hyperbola of one sheet, and the hyperbola of hyperboloid of two sheets, and an elliptical cone. Okay, so those are the options that you have. And for you to recognize things, you need to know things about each one. Ellipsoids, all positive coefficients. Here, currently the z is negative, so it cannot be the ellipsoid. Okay. The elliptical cone, the remaining number, so the leftover number is 0. Remember, the elliptical cone is very similar to the one-sheeter, okay? It's very similar to the one-sheeter. but the radius pinches to 0, which makes the two cones, We talked about this yesterday, about how you compare the elliptical cone and the hyperbola of one sheet. Well, since this number here is 36, that does not have a 0 to it, so it can't be the elliptical cone. Okay? Now, when you look at that one sheet and the two sheet, the one sheet has one negative, and the two sheets has two negatives. So right now, I definitely agree it has one negative in the equation currently, so it's going to feel like it's the hyperbola of one sheet. Do not declare that yet, though, because your issue is you have not moved that 36 over. So I'm going to tell you this up front. It has one negative, so it looks like a one-sheeter, but don't declare yet until you get it in the correct form. Okay, so again, refreshing. All squares, so there's 4 types of surfaces it can be. They're definitely not all positive, or definitely not all negative. They're not the same sign, so it's not the ellipsoid. And the cone has that belt wrapped around at the polar, at the origin, to be 0. And we have that 36, so it can't be that. So it's going to be one of the hyperboloids. And your question is it the one sheet or the two sheet? But don't declare yet. Even though it looks like a one-sheeter, let's get it into the correct form first, and then we can see what it is. So I'm going to take the red equation again. I'm going to copy it. I'm going to, ooh, I just deleted that page, which I did not want to do. So let me run over here. Control Z, did not want to do that. And let me put a new page. And let me paste, and let's solve this problem by getting it into the correct form. Okay? Okay, so first thing, I want to move that 36 over. Okay? So I'm going to subtract the 36 over, and we'll see what happens from here. So I got 6x squared plus 3y squared minus 4z squared equals negative 36. Okay? Now, for the one sheet or the two sheet, each one of them equals 1. So because each one equals 1, let's divide out that negative 36. Okay? So when I do that, I do get the 1 on the right. And on the left, I'm going to have x squared over 6. And now that guy became negative. I'm going to have y squared over 12. And that guy turned negative. And then I'm going to have the z squared over 9, but the negative and the negative makes it positive. Now remember, when I was telling you, we started with one negative, but when I divided by that negative 36, all of a sudden I popped out 2 negatives. Okay? So hopefully you will be able to declare what the shape actually is. And I'm going to write it one more way. I'm just going to rearrange and say z squared over 9 minus x squared over 6 minus y squared over 12 equals 1. Now, that is in the proper form, so you can declare this is a hyperboloid of 2 sheets. Now the question is, I want to graph it. Okay? So if you want to graph it, you have to decide on how it opens up. 2 sheets means a bowl up and a bowl down. Okay? So when you have to decide on that, you're trying to figure out which way it opens up. Is it all over the z, all over the y, or all over the x? Remember, if you're trying to find the opening, you need to decide on the intercepts. And because of the negatives here, it is void on these axes. That's singular. I don't know how to write it plural. So I know it's going to be z squared over 9 has to equal 1. Z squared equals 9, so z equals plus or minus 3. So what I know now is at least it goes up 1, 2, 3, and there's an intercept at 0, 0, 3, and down 1, 2, 3, 0, 0, negative 3. Okay, so you have that. And with the hyperboloid of 2 sheets, you know what it already kind of looks like. It's going to come up and be a bowl, and go down and be a bowl. Okay. Now, if you wanted to be a little bit more specific, if you wanted to detail it just a little bit more, what you could do is you could look and say, hey, all of these traces are ellipses. Okay, so all of those traces are ellipses. So the xy traces are ellipses. Okay, you can look at that because both of the signs of the x's and y's are the same. So I'm going to show you how to get one of those specific ellipses. If I'm trying to make a nice ellipse, what z value could I use to plug in to make that kind of disappear nicely? Like if I plug in 2 for z, 2 squared is 4, so I got a 4/9. I don't like that. So let's see if I plug in 3. So let's look at the ellipse when z equals, and you could say plus or minus 3 because both of them are going to be the same leveling. When that happens, you got 3 squared over 9 minus x squared over 6 minus y squared over 12 equals 1. Let's see, 3 squared is 9. 9 over 9 is 1. So that's nice. That shows me that x squared over 6 plus y squared over 12 equals 0. Does that agree with what we said before? Yes, because that ellipse has no radiuses to it, so it's that dot. Okay. What would be another good z value that could give me a bigger ellipse? So z squared over 9. What could be a nice one with z squared over 9? How about 6? Cool. Z equals 6. Let's try this one out. Again, plus or minus. You could do 6 squared over 9 minus x squared over 6 minus y squared over 12 equals 1. Let's see, 36 over 9 is 4. So I got 4 minus x squared over 6 minus y squared over 12 equals 1. Rearranging, x squared over 6 plus y squared over 12 equals 3. Okay, so that is an ellipse where if you want to be a little bit more specific, you would divide out the 3's. And you have x squared over 18 plus y squared over 36 equals 1. Okay, so that means my y radius equals 6, and my x radius is square root of 18, which is kind of close to 4. And you could go up here, and you could say at level 6, 3, 4, 5, 6. You could plot that specific ellipse, which again was x squared over 18 plus y squared over 36 equals 1. Now that's being a little bit more detailed. The part that I really care about is the z-intercepts and just realizing that it does shoot up. One nice thing to ask yourself is it longer on the y or longer on the x? Football lengthwise, which way is more stretched out? And the whole time, because the y has a bigger value here versus the x value here, every time the y is going to be more stretched out. Okay, and kind of on my graph you can kind of see that the y looks more stretched out, but again that was just me getting lucky. Okay, so let's look at another one here on the next page. So on this one here, I kind of set up again the x squared, the y squared, the z squared, but I don't have any signs yet. So I kind of just want to talk to you about playing with signs. If they were all positives, what would I be? An ellipsoid, okay? If I had them all positive and it went to 0, though, what am I? So it's an ellipsoid, but all my radiuses are 0, which means I'm just the point, the origin, just 0, 0, 0. That one's boring. If I put it as a 4, since the balance of the x, the y, and z are all the same coefficients, it is an ellipsoid, which actually turns into a perfect ellipsoid, which is a sphere. So that would be a sphere with radius 2. Okay? So pluses are kind of boring. Let's add in one negative. If I have one negative, you're the hyperboloid of one sheet, or you are the elliptical cone. And that all depends on the number on the right. If you are a number that's not 0, you're the one-sheeter. And here's why. Okay, I'm setting this up. Okay, let's see, who is the negative? The negative is the z guy, so you're void of z. If you want to set the y and the z equal to 0, you would have x squared equals 4. So x equals plus or minus 2. So up 2, back 2. You could do the same with the y's by setting the x and z equal to 0, and you have the same idea. So right 2, left 2. There is the belt of the one-sheeter, and then it opens up. Okay, so there's the whole thing with your traces being all, and in this case actually they're very nice, they're all circles. Okay, because again the x and y have the same balancing point. Okay, now the only difference is if I go to a 0 instead of a 4, you would do the exact same thing where you'd be setting x squared equal 2, but you'd be doing x squared equals to 0, which means it's at x is 0. And y squared would equal 0, which would mean y is at 0. And when I say it's void of z, it's not void of z when you have negative z squared equals 0. This is the only time the z guy could work because it equals a 0 and the negative doesn't matter. And that turns into a 0. So what happens is it now turns into the cone instead of the hyperbola of one sheet. This red or this blue belt now gets pinched down to there. And what happens with the bending of the blue, it now bends straight to a line. The traces are still circles, but there's no curve to it anymore as it pinched into two cones. So that's kind of good to see that part of it as well. Okay. So that's just a little bit about playing with some signs a little bit, and also the coefficient on the right, or the number on the right. And again, if I'd made it where two of them were negative, you would be talking about the two-sheeter that we had just done before. Okay? On this one, you need to recognize this part of it. Okay? They're not all squares. It's just the y squared and the z squared. And then the x is by itself. Now, sign-wise, I want you to think of this. Y squared is always positive. Z squared is always positive. If you're adding two positives, that means the x value has to be positive. So unlike the hyperbola of two sheets where you had two bowls, now you can only have one bowl because it can only come out of the page. Okay? Plug in 0, 0 works for all, 0, 0, 0 starts this bowl. And the traces, y squared plus z squared. So the traces of the yz's are all circles, depending on the x's. So, and the further out x gets, that becomes the radius of each trace. And so you have that. Okay, so that is called the elliptical paraboloid. A lot of you kind of forget that the radius, the guy that makes the radius of each circle, is this. This is the radius for each trace. So when this is, let's say, at 1, then at 2, and at 3, and at 4, and at 5, if you're at level 5, you already know that that circle, if the x equals 5, that means the radius is the square root of 5, because you'd be having y squared plus z squared equals 5. Okay, so don't lose sight of that, that the further out on the x, the bigger it gets, because that's the radius determining factor. Okay, we're going to keep looking at some more on the next video.